Hi, I'm Sriram. Today I'll be presenting my final project, Recognition of Facial Expressions from Grayscale Images using Convolutional Neural Networks. Firstly, what and why do we need facial emotion recognition? By definition, facial emotion recognition is identifying human emotions by understanding their expressions. It plays an important role in human-computer interactions, can be applied to digital advertisements, online gaming, customer feedback, and healthcare. Particularly, VR gaming requires facial emotion detection for an immersive and real-world-like experience. Driver monitoring systems track emotions of drivers to make sure the driver is attentive and alert, thereby increasing safety while driving. High emotion recognition accuracy has been achieved in images captured under controlled conditions and consistent environments. Challenges persist in naturalistic conditions due to changes in facial pose and subtle differences between expressions. So the goal of my project is to develop a convolutional neural network based model to automatically recognize emotions from grayscale images of human faces. One specific emotion recognition dataset that encompasses the difficult naturalistic conditions and challenges is FER 2013. It was introduced during ICML 2013 Challenges in Representation Learning and became a benchmark in comparing model performance in emotion recognition. FER 2013 is a large-scale and unconstrained database collected automatically by the Google Image Search API. This dataset is hosted by Kaggle and is available for public use. It contains 35,000 examples of faces with expressions such as happiness, neutral, sadness, anger, surprise, disgust, fear. This is the facial emotion dataset I used for my project. You can download the dataset using this link. You will need an account to access the data. I split the data to train and validation sets, 22,000 for training, 5,000 for validation, and 7,000 for testing. Ian Goodfellow, inventor of GANs, reported a human accuracy of 65 to 70% on this dataset. All the images in this dataset are 48 by 48 pixels and they're all grayscale images. Now coming to the technology, as a pre-processing step I normalized the range for pixels from 0 to 255 to 0 to 1. I developed 4 CNN based models. Model 1 is a pre-trained VGG16 model with fine tuning. Model 2 is a VGG style model. Model 3 is a 5 convolutional layer neural network model. And Model 4, the architecture is same as Model 3, but a change to the optimizer. And this change was addition of class weights. Now a detailed view of the different models. Model 1 has 13 convolutional layers and 2.6 million trainable parameters. And I only trained the last convolutional layer of VGG16 just to fine tune it and make sure it adjusts to my data set pretty well. And Model 2 has 8 convolutional layers and about 6 million trainable parameters. Model 3 and Model 4 have the same 5 convolution layers and about 4.5 million trainable parameters. Now if you look into the code, so I use the image data generator to rescale, to normalize my pixel values. And I also added a zoom range that is 10% of the size of my image, that's 48 pixels. And I also added a horizontal flip so that I'm adding basically some variance to my data set. And I did an 80 to 20 split for validation and train set. And you also want to point out that the shuffle, I set the shuffle to be true. because all the samples were in organized in the respective folders. So I wanted the shuffle to be true, so that again I'm adding so that the model doesn't overfit on any one particular class. And this is the model framework using Keras and TensorFlow. Now coming to the optimization algorithm, all models are optimized with the same settings. Stochastic gradient descent with momentum and weight decay was used. Reduction learning rate, I also reduced the learning rate by half if validation accuracy has not improved in the last 10 epochs. I saved the models at the epoch with the least validation loss. And only for model number 4, I added class weights like I previously mentioned. This was due to the imbalance of samples between classes in our training data sets. Since disgust has too few samples compared to the emotion happy, a model without class weights might be biased towards happy than other emotions. The table below shows the class weights added to the loss. This essentially means that during training, when the model incorrectly predicts disgust class, it is penalized heavily when compared to incorrectly predicting the emotion happy. The class weights were calculated using sklearn package. The optimizer was set using the conditions that I mentioned in my previous slides. The performance of models during training is shown here. Model 1 and 2 overfit in the early stages of the training, whereas model 3 and 4 appear to do better because the training and the validation losses track each other very well in model 3 and model 4. Model 4 has the best test accuracy of 65%. The confusion matrix shows performance of of the models for individual classes. Model 4 performs best with emotions such as angry, disgust, fear, and neutral, whereas Model 3 performs well for happy and surprised, and Model 2 performs well for emotions sad. These are some examples of the areas where model assigns higher weights for different emotions. The colored regions are the areas of interest for the model. It's interesting to study the model patterns for different emotions. The model learned to look at forehead and nose regions to recognize anger, whereas cheeks region to recognize disgust, and hands to recognize surprise, whereas lips to recognize the emotion happy. I wanted to also show some challenges that the data set has and the model failed. I added the label and prediction for all these images. Have a look and see if you agree with the model or with the label. Especially, with Obama's expression here, where the label says fear, but it could have been sad or it could have also been neutral. And in this instance, where it says fear again, and the model thinks that it's a neutral expression, which I totally agree with. And for here, the label says Obama was surprised, but again, the prediction said sad. And here too, where the label says that this person is happy, but the prediction is sad, which I agree with the model again. So that was my project. Thanks for the opportunity. Thank you, Professor Zoran and the TS for offering this course. It was really helpful. Thank you.